Hello and welcome to this Manufacturing Process Technology Part 2 Module 1. I am Shantanu Bhattacharya. I am an Associate Professor at the Mechanical Engineering Department at the Indian Institute of Technology at Kanpur. So prior to this we had also done another series of courses related to manufacturing systems and then Manufacturing Process Technology 1, where we had talked about the primary manufacturing process like casting and some of the joining processes, secondary manufacturing processes like welding or machining technologies. Here in this module we would focus on more towards the advanced machining techniques which have emerged because of a diverse amount of new materials which have emerged because of again the aerospace and the automotive industry requirements, and also the requirements that have been generated to produce very complex parts with geometries which are very complex and otherwise cannot be achieved using conventional machining processes. So this module would actually be an introductory module for advanced machining processes, and then once we are able to cover all these processes in details, which will include models, which will include the different applications of such processes, we will delve into the metal forming area and try to do a few modules in that particular area or domain. So let us look at a brief introduction of advanced manufacturing processes, why they are needed. So parts which are manufactured by casting, forming and various shaping processes require further finishing before they are ready for use or assembly, and that is one of the main reasons why these advanced manufacturing techniques were developed actually. So in many engineering applications sometimes interchangeability of parts is a big requirement, okay, and this is needed. We need specific tolerances, dimensional accuracy, surface finish, so on and so forth, and they are very vital for making a family of parts or a group of parts which are uniquely similar. They have similar manufacturing processes and they can be used in a variety of area. Look at, for example, fasteners in automotive industries. So therefore the surface finish definitely becomes a very critical issue in such parts, and we have to go for some non-conventional type of material removal processes which would enhance the surface finish or which could actually give dimensional accuracy or more tighter tolerances to the systems or parts. So machining involves the removal of some material from a workpiece, as you have done before, in order to produce a specific geometry at a definite degree of accuracy and surface quality. And we will now try to look at some of the issues related to the history of how machining emerged as material removal processes emerged. And if you look at historically, the first kind of tools which were used by mankind were used mostly or made of by bones, sticks and stones, and there were hand tools, and if you look at historically about 2.6 million years ago, the first Paleolithic stone tool industry, the older one, was developed by the earlier members of the genus Homo habilis. This contained things like choppers, burins, awls. These are two stone implements which are formulated back in those days, which can be considered to be the first tool or first machined tool. So as gradually things moved forward in the upper Paleolithic age, there were little more advances to this simple choppers or burins, and they were replaced by these nets or bolas, which typically would be hurled around in a stone, and it would be thrown off so that it would be typically used as a hunting tool for most of the food requirements that were present. So this followed by development of the spear thrower, bows and arrows, so on and so forth, and that is how the historically significant stepping stone towards material removal processes was met. This followed by later on by a series of developments, and if we really look at 1 million years back in the Bronze Age, there were many tools and weaponries which were used from different shapes and sizes. Man now knew how to actually melt and cast. Then there was this ceremonial giant dirk which was found in France in 1500 to 1300 BC, belonged to this particular regime, and all the tools up to almost about the 17th century were man-made, or they were made using hands or handheld tools. The first introduction of power tools came way back in 1774, which was basically in terms of a precision boring machine for engine cylinders, as you can see right here. And this was one of the first instances when machines started to be powered with alternate sources of energy like steam, okay, or water, and later on electricity as age progressed. So there were many other examples during this time. 23 years later, Henry Maundsley further made advancement in machining when he devised a screw cutting engine lathe. James Naismith invented the second basic machining tool for shaping and planing. You can see some of the examples here: the lathe, the shaping planing machine. The first universal machine, a milling machine, was built by J.R. Brown in 1826. This shows one of the very first models of such a machine. And then in the late 19th century, the concept of precision came into being because of the introduction of processes like grinding, which would give a surface finish and a surface tolerance, so that parts could now produce function more appropriately in assembly of parts. So an advanced form of this process now is lapping, for example, or honing, and it's used to produce high quality surface finish and very tight tolerance. So that's how I would say machining progressed. And if we look at some of the current trends, particularly towards the later part of the 19th and 20th century, machine tools became increasingly electrically powered. Basic machine tools had further refinements. For instance, multiple point cutters for milling machines were introduced. So this would make a high yield machining process. The whole machining paradigm was controlled by skill set dependencies of the operators, and therefore in order to make repeatability or of producing parts a mandate, the first CNC machine was introduced, which started with numerical control in 1953. So this led to a series of these computer numeric control machines and direct numeric control machines, and then later on distributed numeric control machines, which were step by step improvement of the basic NC machine, which was generated at the Traverse City by the Parsons Corporation in the year 1953. So the present capabilities of these toolings are enormous, with almost a machining accuracy or a finishing accuracy of close to about plus minus 1 microns. And not only that, they have huge capabilities of producing complex shapes of parts, which makes this set of NC machines a very useful set of tools for the future machining aspects. If we look at the modern machining practices, they really emerged because of the increasing requirements of two different industries, that is the aerospace and the automotive industry, in terms of more stringent engineering requirements to be met by the parts, harder, stronger and tougher materials, and a lot of research was invested in the area of materials engineering alone, and it became very important to be able to finish or machine extremely tough and lightweight materials. So these were one of the reasons which resulted into the formulation of the so called advanced machining or non-conventional machining practices, and they were so very different from the traditional machining domain that now we were talking mostly about applying energy in different forms, like let us say mechanical packets of energy or thermal packets of energy, or probably packets of photons or quantum of light, using them or these different methods as, or even chemical energy. There were a series of very highly complex shapes and integrated surfaces and also miniaturized elements which actually could be formulated by these novel conventional, non-conventional or advanced machining practices. So as a corollary of it, micro machining also emerged, and because of this change of capabilities, obviously you could go at smaller sizes and be able to finish better at those sizes. And so therefore a domain of engineering involved, which is also known as the micro machining engineering, where a lot of parts of the size of less than in the sub-millimeter zone could be realized very accurately. So recent applications of micro machines involve silicon glass micro machining, excimer lasers, photolithography, so on and so forth. So if we really put together some of the modern forms of machines and historically look back, we started with precision grinders with an accuracy level of almost plus minus 1 micron of the surface finish. This generated a series of tools which were enabled to measure such kind of accuracies, and mostly using lasers or optical fibers such tools were realized with different forms of light patterns or interference of light through which we could actually produce reflections and try to correlate the topography of a surface with respect to the signal that was generated, so on and so forth. So we had a set of high precision metrological tools or advancements which came into picture, and then finally this resulted in nano machining, which is very recent trend in these processes. And in this particular process it was more about the successful manipulation of atoms or molecules which could not be otherwise possible in a conventional machine. So the precision that was needed was even much higher of movement or relative movement in comparison to what it would be when we talk about conventional machines. So nano machining or nano finishing processes came towards the probably the beginning of 19th century, and it was 20th century, and it was introduced by Taniguchi to cover the miniaturization of components, and this would typically mean achievement of tolerances in the range submicron level to that of individual atoms or molecules, that is between 100 nanometers to 0.1 nanometers, or almost 1 Armstrong or 1 atomic spacing thick machining. So in fact, starting from Taniguchi, he kind of mapped the different machining accuracies way back in 1983, where the scale here on the y axis shows the machining accuracies in micrometers, scale on the x axis shows number of years as the machining technology has progressed, and you can see here that accuracies from 100 microns to 1 micron typically come within the normal machining range, which includes typically machines like turning milling machines, grinding machines, CNC machining centers, lapping and honing, jig boring and grinding mechanisms, so on and so forth. Then we have the precision machining domain, which comes from 1 micron to 0.01 microns, which actually includes optical lens grinding machines, precision grinding, super finishing, diamond grinding, turning, high precision mask aligners, ultra precision diamond turning tools, turning and milling machines, so on and so forth. And then finally the final ultra precision machining, which varies between 0.1 microns all the way to 1 nanometer and even beyond, where we talk about really some very interesting developments of the current century, depending related to electron beam machining, soft X-ray lithography, ion beam machining, molecular beam epitaxy, ion implantation system, so on and so forth. And this really is able to produce accuracies almost at the atomic lattice separation level. That is how highly accurate the machining strategies can be in this particular kind of material. And then of course you can actually have self assembly techniques or material synthesis technique with a bottom up approach, which can even go further and be able to produce 1 atomic layer thick material uniformly over a surface to give that kind of a precision to that particular surface. So that is how the machining accuracies proceeded on a year wise manner, starting from 1940 to 2000, almost the current century. And you can actually map in terms of different grades of machining and some of the accuracies, the various technologies that have emerged or been formulated. So let us now look at some of the classifications which are involved in material removal processes. And if you may recall, earlier we had focused more in the part 1 of this course on the traditional machining domain, where we talked about various cutting processes, turning, boring, drilling, so on and so forth, and then various shape making processes like milling, shaping, planing, broaching, sawing, filing, gear forming, gear generation, so on and so forth. The second part of traditional machining belongs to mechanical abrasion, where we talked about bonded abrasives, grinding, honing, coated abrasives, loose abrasives, polishing, buffing, etc. And then in this particular module we will be more focusing on to this non-traditional machining, which is really going to be the area of interest for at least the first few modules when we talk about the various processes like chemical machining, electrochemical grinding, electrodeposition machining, laser beam machining, abrasive jet machining, water jet machining, plasma beam machining, ultrasonic machining, so on and so forth. And also we will try to introduce some of these in context of microsystems engineering or microsystems fabrication processes, talking about a little bit of deposition or lithography driven approaches for doing small materials fabrication or small micro nano fabrication, so on and so forth. So that is going to be the mandate of first part of this course, manufacturing process technology part 2, and would just like to do a little more detailed classification. So as we have already realized, in conventional machining processes, the tool is penetrated in the work material, particularly to the depth of cut, and there is a relative motion between the workpiece and the tool, and that determines really the eventual geometry that the workpiece is shaped in. And examples include things like turning processes, particularly turning of cylindrical parts, shaping and milling, which generates mostly flat surfaces, drilling, which produces holes of different diameters, etc. And the major important parameter here to be safeguarded as basically the temperature, and temperature generated at the machining zone is really advantageous for higher productivity and better finish, primarily because the workpiece material reduces in strength and ductility because of the high temperature, and it comes into the plastic flow state. So in fact, if we look at literature back, Elcaddy et al. In 1998 claimed the formation of a continuous chip from discontinuous ones due to the workpiece prior heating, and in Todd and Copley in 1997 built in fact a laser assisted prototype to improve the machinability of difficult to cut materials on traditional turning processes by focusing a laser beam onto the workpiece just above the machining zone, so that it could reduce the cutting forces and improve the tool performance. Okay, so all these different couplings of the sort of, you can say, modern domain of non-conventional methods kept on carrying out throughout the 20th century. And typically if we look at all the metal cutting processes, I think I had illustrated it earlier also in my lecture, that during machining by cutting, the shape of the workpiece may be produced by forming. When cutting tool possesses the finished contour of the workpiece, you can see exactly the negative of whatever you need to achieve on the surface. Here a relative motion is required to produce the chip in addition to the tool feed in depth. And then there are generation processes. Okay, so this is a shaping process where the inverse of the tool shape is impregnated onto the machining surface, and generation where there are several motions that accomplish a certain geometry or a shape. For example, in the case of turning, you realize that there is a linear motion of the tool and a rotatory motion of the workpiece which generates some kind of a cylindrical surface, or things like frustrum shapes, or even symmetrical shapes which are symmetrical about the axis of rotation of the workpiece. There are actually combinations of shaping and generating processes. For example, this process right here shows there is a form and generation cutting where there is actually a shaping operation going on and also a cutting operation. The shaping actually is in terms of getting this shape, which is exactly the reverse of the cutter, and the cutting process of course is the chip removal process in this particular case. So that is how you classify all these metal cutting processes. And when we talk about machining by abrasion, as we are aware that this is the machining where the machining allowance is removed by multitude of hard angular abrasive particles or grains. This was in fact invented at the beginning of 20th century, and these grains are also known as abrasive grits, which may or may not be bonded to in the shape or form of a tool of a definite geometry. And in contrast to metal cutting processes, during abrasive machining the individual cutting edges are randomly oriented and the depth of engagement is small and not equal to the abrasive grains that are simultaneously in contact with the workpiece. One of the reasons why you can have more higher level of finishes because of this particular methodology of material cut. So in fact the material in this case is removed in form of minute chips, so minute that it almost gets immediately oxidized, and goes up as splinters of flames, and they are invisible for most of the time because of the high temperature and subsequent oxidation of the chip material, which is dislodged from the surface. So, various categories of abrasive machining are included, where the metal abrasion action is adopted during grinding, honing and super finishing processes. They employ either a solid grinding wheel or a stick in form of a bonded abrasive. For example, in this case you can see this honing stick, and there is a bonded abrasive onto the honing stick, which actually rubs against the workpiece in presence of machining oil. Okay. And similarly, you have one level further in terms of finishing capabilities, the process of lapping and polishing and buffing, where there is in fact a loose abrasive medium which actually is sprayed on the workpiece, which is rubbed with a buffing tool or a lapping and polishing tool. In fact, these are processes typically used in the paint industry, particularly automotive painting, where there is a high level of polishing as well as dust removal and other defect removal mechanisms which are employed. So, they use a lot of this lapping, polishing and buffing techniques. So, that is how abrasive machining is categorized. Now, let us look at non-traditional machining. So, in fact, they are classified based on what is the kind of energy application mechanism which leads to the material removal, and needless to say that because of the complexity requirements or material strength requirements, these came up. So, in general, non-traditional machining processes are classified into processes that would apply mechanical energy to remove the material. The categories would involve machining methods like ultrasonic machining, water jet machining, abrasive water jet machining, ice jet machining, so on and so forth. Materials that or processes that would employ thermal means to dislodge the material either as a melt or as a vapor. For example, electro discharge machining, electron beam machining, laser beam machining, ion beam machining or plasma beam machining. And then there are processes which are either using chemical or electrochemical means to remove the materials, where it could include chemical machining, photochemical machining, electrochemical machining, etc. And is typically single action non-traditional machining processes, where there is one of the strategies which are used for removal of material, although in the current domain we have a combination of strategies called hybrid machining approaches, where more than one processes could be used simultaneously for obtaining a better surface accuracy or a better surface finish. So, this is going to be the domain now, and we are going to look into the individual levels of the different processes, starting with some modeling, some approaches related to this, and this we will cover probably in the next module. Thank you.